Okay, so it's my pleasure to introduce Christian Ikenmeyer, my former PhD student. He is now postdoc here at the Science Institute, but he has a position at Texas A&M and works with Joseph Landsberg. And he will tell us today about geometric complexity field tensorings.
Thank you very much, Peter. Okay, this is about GCT and tensoring. And Peter already gave a talk about this topic. So this is, of course, all joint work with Peter. So, and well, we want to. I want to present to you these in more detail these abstractions that we found in the tensor rank setting that give us a lower bound for the border rank of matrix multiplication, which is a non-trivial bound. It's not the world record, but it uses basically all the methods from GCT that can be applied at the current time. So it's a generalization of something. So I recently found out that this is actually a generalization of something that Strassen found. So a theorem by Strassen is that there are degree 4 equations vanishing on border rank 3 tensors. Okay, and now we generalize this. There's degree 4 equations vanishing on border rank 3 tensors. So doesn't matter, in some Cn, tensor Cn, tensor Cn. And n is large. Okay? So
what 3 stands for? It's for border
rank 3.
Border rank 3.
Border rank 3. Border rank 3 tensors. Those are border rank 3. Thank you. Okay? Okay, so we would want to generalize this. We want to have things vanishing on higher border rank tensors. Okay, so this is a generalization now. And we generalize this to degree kappa. Oh, the degree is a bit higher. It's 3 kappa plus 1 equations. This is the equation, and it vanishes on border rank 3 kappa. Okay, so
Do you find all or some?
Some. I just find some, and I just take these and generalize them. I don't say anything about I found all or something like that. So the space we are working in is this.
Exactly?
On border rank less or equal to. Yes.
Exactly.
Okay.
Set theoretically or scheme theoretically.
You're not saying they're cutting.
No. We just find some. This is just.
Yeah, right.
Actually, yeah, this is just one equation actually. So because there are more equations, but it's not clear that those are all. It's just some degree 3 kappa plus 1 equations.
What relation
So it's not
between kappa
exactly that.
Sorry.
What relation between kappa and n?
Let's just n be large. N be large enough. Just n be large enough. Kappa is not depends on that. And okay. What do we get from that? We will get a border rank. So the result of this will be a lower bound here of the border rank of f times a matrix multiplication of, and then we have to be a bit careful. There's some subtlety here. There's a -2, but yeah. This will be the lower bound. So when you have this equation, you plug it in, evaluate at the matrix multiplication tensor, you get this lower bound. But we will see how this occurs. So and this and also one feature of this is that since this method is very combinatorial and it's not very geometric, it also works for the support rank because there's no So it actually only uses the support of the tensor. Okay, so let me explain to you how this works and what's used to use. So this is our space, and we have a group action. That's GLN cross GLN cross GLN. And yeah, let me call this group GLN cube. In the obvious way, like so the first GLN x here, the second x here, the third x here. Okay, and now there's the unit tensor you might have heard about. So I'll write it this way: it's E sub n. Yes, so it's the sum I equals 1 up to n ei tensor ei tensor ei. And we always think of embeddings. We embed. So I always do this. So just so there's no confusion about the different spaces. So this one is embedded in C2 tensor C2 tensor C2, and this one is embedded in C3, and so on, right? So you can just, if you think of just tensors as boxes or numbers, that's very natural, and you just have larger boxes. So you just fill up with zeros if you don't have enough. You just can always embed like this. And now the orbit closure. You take your group GLN cubed and let it act on En, move it around. This one is the set of border rank at most n tensors. If they, I mean, up to some technicality here. It's the set of border rank less or equal to n tensors, up to some technicality. And the other tensor that we want to compare this with is the matrix multiplication tensor. So the matrix multiplication tensor is defined as this ijk going from 1 to m. And now you have a double index on your basis. Just choose any nice way of indexing it. That's your matrix multiplication tensor. And you want to prove now.
N is squared. M has to be squared now, right? N is squared.
This one here? No, this is I, J, and K running from 1 to M, and this is double index. This is a double index, so those are, yes, this is a double index. So it's
Cm becomes Cm is squared.
Yes. So what you get is these are just basis vectors in Cm squared. That's exactly correct. Thank you, Shawan. Okay, and there's where this tensor lives, and now your n. Normally, your n would be larger than m squared. You know, so you want to just know how can I somehow this tensor lives somehow in some. Of course, lives in Cm squared, tensor Cm squared, tensor Cm squared, right? So it lives certainly here, and you want to have some larger n. You want to, yeah. Let me precisely state the question. So we want to find n as large as possible such that the matrix multiplication tensor is not in this orbit closure. Okay, that was the setting. And now, because that's the border rank, that shows basically a lower bound on the border rank of this tensor. So, well, and the point is, of course, if we want to do geometric complexity theory, we do this by exerting some function in the vanishing ideal and want to evaluate this function on this tensor. So that was the idea. So it's, let me just restate this. So it's not in there. If there exists this polynomial f, it should be in the vanishing ideal of GLN cubed En And it should have, so it should vanish on all these tensors of this border rank, and should have this property, should not vanish on the matrix multiplication tensor. Right? This would be nice. So, and the first proposition is that we don't have to consider all the polynomials, but we can, so proposition is we can restrict our search considerably using representation theory. And this is also what makes the whole thing combinatorial in the end. So the proposition is we can restrict, f can be taken, right, let me say, f can be taken from an irreducible representation. In this vanishing idea. You got, so there's structure on the vanishing idea. And we can use that. So the vanishing idea actually, well, let me write it down, it decomposes. Let me write it down. So the vanishing ideal decomposes into irreducibles. Say, I don't know. And those are just irreducibles here. And we just pick. We can just always pick a f that is actually a vector in some irreducible representation. This decomposition is not a unique decomposition, of course, but the isotypic decomposition is, and well, so, but that's not the point at the moment. So just.
No, it's 3 copies of GLN.
It's GLN cubed is 3 copies of GLN. So this is the group that is acting is GLN cross GLN cross GLN, and it acts, so it acts as follows. So if you have a G1, G2, G3, it acts on, say, V1 tensor V2, tensor V3. So by definition is G1 V1, G2 V2, G3 V3. That's how it acts.
Yeah, but V1, V2, V3 is in CM.
Oh well. If GLN, then this is in CN. So these, yes. So those are in CN. So
Right. So they are in CM. But this MM is in CM square.
yes, that's right. And
So I'm a bit confused.
yes, but I embed this. So I embed all these spaces just into the larger spaces.
He's just confused with.
No, that's it. I think. You just make it larger. It's fine. You have the larger group acting.
Then I will put n squared.
Yeah. So yes, n is greater or equal to m.
Line.
Yes, that's that.
I didn't read N.
Okay, I'm sorry. N is the larger one. It's so yes. You can embed this, and then this all becomes well defined, right? And you have the tensor sitting there. Okay. So that's the first proposition, and so the proof of this proposition is also very easy because you can just, if you have an f, so proof is just if you have an f, you decompose it with respect to this decomposition that you have, and then you just take one of the summands, and that's a summand in an irreducible representation. So there's actually nothing to this. If you know that this decomposes, then that's it basically. So basically, the only thing that you need is that this group is a reductive group. So all your representations they decompose. Well, that's nice. And so.
You're just saying that f is the highest weight vector, is it?
Yes, basically. Well, at the moment not, but you can restrict yourself. So that's the next step. You can restrict yourself actually to highest weight vectors. Yes. Not everything is a highest weight vector there, but you can restrict yourself because these irreducibles are actually defined basically by their highest weight vector span. So what is that, a highest weight vector? So that what Ketan said is that you can actually restrict yourself to highest weight vector. So what is that, a highest weight vector? So let me explain to you what that is. So T is the torus. So it's just these matrices, diagonal matrices, and take triples of those. The determinant should be also non-zero. That's the torus. And U should be the unipotent. This group having ones here on the diagonal, this star here, and also take triples of these. So these are your two groups. And now, first of all, what is a weight vector? So a weight vector is something that is some vector that gets scaled if you apply an element of this torus here. So a weight vector f of weight. And now what is a weight? Say this is some lambda, and I want to write, so my notation gets, otherwise it gets clumsy and crowded. So I want to see lambda will be 3 partitions, but I just want us to see this as these 3 partitions is a long set, as just some numbers, and those are 3n numbers. Okay, it's just 3 partitions just concatenated. So a weight vector of weight lambda. So lambda is a tuple of partitions. What does it satisfy? It satisfies the following. That's basically the definition. So whenever you have a diagonal matrix, so for all T1 up to T3n, that's your diagonal matrix, and you let this one act on your F, 3n acts on F, what should it be? It should just give T1 should be raised to the lambda 1 power until T3n should be raised to the lambda 3n power. So it will be just scaled. So your F will be just scaled. That's a weight vector. And now if additionally we have that all these group elements in U yeah, because okay, that's because I'm only interested now in polynomial representations. Okay, yes, because at the end it all comes down to polynomial representations anyway, so that's why I don't care about the others at the moment. You can just always replace the inverse with the transpose and everything works always, and you always have natural numbers. Everything works. Okay, so for all group elements in U, you want to have that your F is fixed under this operation, under all these operations. And this is now, if additionally this holds, we call F a highest weight vector. And the point I want to make is, well, this looks very complicated, but they have a very combinatorial description, and this is what I want to show you now. So those have a really nice combinatorial description. Okay, so first of all, the most important things, why do we care about highest weight vectors, is the following, because every irreducible representation is nothing more than just the span of the orbit of the highest weight vector. So we can restrict ourselves actually to highest weight vectors. That's a proposition. Every irreducible cube representation is the linear span of the orbit of the unique highest weight vector in there. So this means we can restrict our search to highest weight vectors. This almost means we can do that up to some group.
Unique up to your scale, right?
Yes, unique up to yes, thank you, up to scale. Yes, that's true. So we can restrict our search to highest weight vectors. Now, what do I mean by that? I mean that that when you only take the highest weight vectors, but it might be that you have to apply some group element, but that's not a serious issue. So basically, we are interested in highest weight vectors. So now the point is that these polynomials have a very interesting combinatorial structure, and you can basically do everything combinatorial. You don't have to think about all these things anymore. It all works completely combinatorially, and I want to show you. I don't give you the proofs for this, but I want to show you what kind of arguments actually work here. So the dimension of the highest weight vector space highest weight vector space of weight lambda inside our coordinate ring of what we're actually interested in. So this is the third tensor power of Cn, right? This is what we're interested in at the moment. And say in degree d, this is the space of all these highest weight vectors, which is the same as, so the dimension of this highest weight vector space is the multiplicity of this irreducible. Is the same as basically, you can also define actually multiplicity like this. So it's the multiplicity of lambda occurring. So how often does this irreducible occur? And this is called, I call it k lambda, and this is the Kronecker coefficient. So this is the first interesting observation that we get from highest weight vectors here. And now we can be much more explicit.
Can I just ask one question?
Yes, sure.
So, when this number of factors is not constant, is the Kronecker coefficient still in gap P?
When you have more than 3 factors, you say, or what?
Yeah. Is it still in gap P?
I don't know. I would have to look at that. The number of tensor factors. So then you have an iterated.
I think so.
I would think that these formulas.
That's the same. It's still in gap P because
I think it's not obvious. I mean, I think you can I would think that you can generalize the formulas, but that we have. Okay, you think it's okay? Well, it's not okay. Okay, this is the Kronecker coefficient, and that was a specific question about it. Okay, let me. So you can now very precisely say what is the combinatorics here, and it comes from sure wide reality. It says that there's actually this vector space here, a basis, a generating set is given by of this space. Let me I should have given this a name. This is the highest weight vector space. Let me give this maybe this is now highest weight vector lambda. A generating set of the highest weight vector space is given by triples of tableaus. And this is of shape lambda. So lambda is a triple of partitions, so this makes sense. You have lambda is a triple of shapes. So for example, so the degree of this whole polynomial will be the number of boxes. So this is Strassen's. This is Strassen's equation. You can write it with these tableaus. I will show you how you can see with these tableau combinatorics that this actually vanishes on the low rank tensors. So this is by Strassen. And the Kronecker here is actually also 1, so it's a unique thing. So, okay, so it works as follows. We want to, so I want to interpret this one as a tensor actually in the tensor space of the vector space of tableaus. So you have tableaus here, and tableaus here. And whenever I write a tableau, I want to think of it as a quotient space, quotient by the Grassmann-Plücker relations. I don't want to explain the whole Grassmann-Plücker relations now because I did that in the bootcamp, but we only need a single Grassmann-Plücker relation here. So this here, Grassmann-Plücker relations, and there's only a single one that I want to talk about. And this is the one where, when you have a tableau, think of it as a vector, you switch 2 boxes that lie in the same column, then the tableau switches sign. That's the only thing. Yes?
I just don't miss. So highest weight vector is just vector in C of like
No, it's a vector here, so it's a vector here in this space. Yeah, it's in this space here.
Christian, I'm a bit
but what's the correspondence between
The correspondence is Chauvet duality.
between these diagrams that you wrote and this vector space?
Yes, there's a correspondence. It's called Chauvet duality, and I will tell you how to evaluate such a thing.
So what is this matrix? Is it like Young tableau?
Matrices. This is a Young tableau. This is a Young tableau. This is Grossman-Plücker relations on Young tableaus.
Christian, I have something that is not
Yes. Yes.
Grossman's examples, he gave semi-invariants. So the corresponding partitions are rectangles.
Oh, but those are other Strassens equations. There are different Strassens equations. So not the rectangular ones. Yes, it's not. That's not the ones with the 9 boxes. This is a different ones.
Strassens equation.
Could be that. It's just that.
Strassen.
Oh, there are more. That they
The
are.
one that I
But those are in higher degrees. Those are in degree 9, right? Because they have 9 boxes. So those are lower ones.
okay, but they are not semi-invariant, so I see. Okay, good.
They're not invariant under SL. No, it's not.
So
Those are different.
each Young tableau corresponds to vector in C of Cn.
No, it's there's a.
I know how to make tensors of vectors.
Yes, it's a tensor of tableaus. A tableau is in a tableau space. There is the connection is that you go from the dth tensor power of the third tensor power of Cn, and you decompose this using Chauvet duality, and then you have these constructions. Well, this would happen, so you have to make all these steps formally. So, and then you see that you have a highest rate vector space. It's one-dimensional, so you can basically do everything over the symmetric group, and it acts here. So I just wanted to tell you the combinatorics of these vectors.
Here there's a shorter answer, which is there is a map called Young symmetrizer, which takes that as input and produces a polynomial, which is in polynomial ring on tensors.
Oh, that's a nice answer. This is a nice answer. Thank you very much. You take this Young symmetrizer corresponding to those. That's nice. And then you also get the same thing. Okay, how does evaluation work? Because that's the important thing. So the important thing is, why does this thing vanish on low-rank tensors? So the first thing is whenever you have a tableau, for a tableau T, I want to impose the following thing. So when you apply pi to T, then this should be the sign of pi T, so it should just not change for pi commuting inside the column. That's the easiest Grossman-Plücker relation. So you would have that this over there, 1342, is actually minus 3142. And in particular, you have that things vanish now. So for example, the easiest example that you get, so this tableau is actually 0 because it's minus itself, right? This is why it vanishes. So it's 0. And now, well, the magic is that you can actually evaluate it. So you can say there's a property when is something like this in the vanishing idea of the unit tensor. So this vanishes if and only if the following vanishes. You take the sum of all phi, those are mappings from the set with D elements to the set with R elements, and you just apply phi to the tableaus. And that's it, basically. And if this vanishes, then this is a thing in the vanishing idea. This is the only thing that you need. And what is this? What is phi? Phi is a map D. So this has D boxes. In this case, it's D equals 4 boxes.
Why do you write f in I equals 0?
Sorry. I only meant f is in the vanishing idea if and only if this vanishes.
Why is that true? Did you say that?
No, I just stated it. Okay? I just stated this. Okay? So what happens is, so this is the common.
If it's highest weight there?
Yes, f is here a highest weight vector. Just take a highest weight vector, take this highest weight vector corresponding to this tableau tuple, then this is the combinatorial condition that you need for vanishing on low rank tensors.
What is your condition now?
The condition is you have these three tuples, you apply your phi, it's a summation of all maps, so all assignments from numbers 1 up to d, so from all these 1 up to 4 numbers, to numbers up to r, which in our case would be 1 up to 3 only. R is, you want to, oh, sorry, it's n. You're right, sorry, it's n, should be n. So it should be 3 in our case because we want to somehow want this to vanish on rank 3 tensors. So you plug in numbers here, and you replace your numbers by other numbers, right? And then you see, then you want to show, want to know will the sum vanish. That's the only thing that you have to do.
That's just the evaluation of the,
yes.
the polynomial on En.
Oh yeah, of course. Of course, it's exactly that.
Evaluation of the
If you know how the evaluation process works, then this is exactly, of course, the evaluation. Yes, there's nothing deep in here, of course. It's just you have to explain the whole evaluation process. Okay, so there's not a deep theorem here. It's just the combinatorics that are involved when you construct these with these symmetrizers. So now you see why this actually vanishes, because now you apply, well, if you draw this as if you draw all these relations with a picture, say this is a 1, 3, and 4, they lie together in one. So they lie together in the same thing. And there is a 2 here. So you have 1, 3, and 4. Those are grouped together. And you have 1, 2, and 4. Those are grouped together. And you have a 1, 2, and 3. Those are grouped together. So now your task is to assign, so phi assigns to these numbers less numbers. So you only have 3 numbers left. So you want to assign 3 numbers such that this thing here never occurs. Because if this occurs, then your summand vanishes, right? You sum over all those phi, but you want at least one summand that is non-zero, right? You want to have something that does not look like this. But the point is, it will always look like this because you only have 3 numbers now that you can put here. And the key property is that every pair of numbers lies in some hyperedge of this graph together, which means every pair of numbers you find somewhere in one of these columns here, so this vanishes. So that's basically the argument.
Maybe can in this example d equals 4?
Yes, it's d equals 4, n equals 3 here.
N equals 3.
Yes, it's d equals 4, n equals 3. So now, okay, this does not matter at all. I mean, you can replace these numbers just by dots now, just for a second, to see how this easily generalizes. So you put a dot here, and a dot here, and a dot here. And this now, the whole argument easily generalizes. You put just more dots. Put another dot here, another dot here, another dot here. And we added 3 to our degree, which basically means just you put numbers here, like 5, 6, 7. 5, 6, 7 should go here. Well, then this is the 5, 6 construction, so you want to have a 5, 7. So we want to keep this property, right?
Maybe good to mention what you're doing conceptually as well as the detail.
Oh, conceptually, I raised the degree, but the same combinatorial argument works. So I raised the degree, but by the same combinatorial argument, this completely works. So it's still vanishing on rank 6. This one, in this case,
d equals 4, n equals 3, maybe.
that's gone now. So this is now.
Y is 0. It was.
Yes, I can say that again. Why this is 0? So you place your numbers here, but you only have 3 numbers. You place your numbers like 1, 1, 2, 3, or 1, 1, 1, 3, or any way. Doesn't matter. This is phi. You sum over all those phi. But then one of your factors, so these are factors, one of your factors will vanish because there will be 2 numbers that are the same and they will lie in a hyperedge with each other. So which means they are lying in a column here with each other, which means they vanish. That's the point. So 3 are not sufficient here, which is basically the chromatic number of this hypergraph is too low. So you cannot really put these things. So they, yeah. That's basically the argument. The argument is actually so the chromatic number of this hypergraph is too low. This is why it vanishes. And you can generalize it by just upping the degree pretty easily, by just putting more things in here. And this gives you exactly the hook triple that gives you this obstruction. This gives you exactly this vanishing property. And this is a periodic combinatorial, so this gives us a lower bound that is actually also, it's not only working for border rank, it's also working for S rank, for example. So all these.
Show that there exists something non-zero. That it is.
Yes. So let me. Yes. So that's also, of course, important. So, but let me just say.
Same strategy for showing it is non-zero and matrix tensor, is it similar?
If you want to show non-zeroness, of course, on the matrix tensor, and that's just.
Similar strategy, is it?
It's the same strategy, but it doesn't. I mean, it's not as easy because it doesn't come. It's more technically involved. So let's just put it that way. But yeah, we managed to do that. So checking that f is non-zero here on the matrix multiplication tensor is non-zero is technical involved. It's just a long thing to actually pull this through.
No, where is the bottleneck because of which you can't go over 3 by 2 here?
Sorry? Oh, 2 by 2.
No, whatever you get lower bound, there is some bottleneck because of which you said there is some Tarski's conjecture because of which.
Oh, yes. Let me tell you that.
See that bottleneck.
Yes, the bottleneck is the following. So we can, well, this is an argument just that something vanishes, but this is certainly not the only argument that you can make. And if you only want to use that argument, using only this argument, this argument is chromatic number is too low. Right? Only this argument, then a conjecture by Alon and Kim implies that we cannot get better than that the leading coefficient cannot get better than 3 over 2. Of the lower bound cannot exceed 3 over 2. But this is if we insist on using this kind of proof.
Yes, but then there is no inherent bottleneck.
No, there's no inherent bottleneck. So this is actually if this lower bound exists, then these kind of linear combinations of these tableaus must exist.
No.
This is just this very simple method of proving that these highest weight vectors vanish on tensors of small border rank. This is a coloring argument. This is not no linear algebra.
Okay.
So when you say this argument, do you mean this argument for showing the chromatic number is low, or do you mean the idea that the chromatic number is too low?
The chromatic number will just not be low. The chromatic number you cannot. This is a conjecture about chromatic numbers.
Okay.
And yes.
Yeah, and also,
Yes.
when you say this idea, you mean some particular shapes or like arbitrary shapes?
Arbitrary shapes. I mean arbitrary shapes.
Only triple products of tableau, not linear combinations.
This is only, yes, this idea uses not linear combinations. This is exactly only these and chromatic numbers. So it's very limited, but still works. Or linear combinations of tableaus. You can use linear combinations of tableaus. Which is, so in general, it's not clear that a single triple of tableaus gives you anything. Normally you would have to have linear combinations. But in our case, so okay, let me state one more thing. So this one here, that the Kronecker is 1, this is true for all our cases. So also for the larger ones, so it stays 1. And this means basically that this is an occurrence obstruction in the sense of the GCT program, because there is only a single highest weight vector up to scale, and that one vanishes, which means all of the highest weight vectors vanish, because there is only one, so this is an occurrence obstruction. But this is basically the reason why it is an occurrence obstruction, because this stays one orbit. Yes, I can, yes, so. This is only, because this is 1, Kronecker coefficient of lambda, so this is the multiplicity of lambda in the ambient space, and if you prove that the highest weight vector lies in the vanishing ideal, then the whole isotypic component, of course, lies in the vanishing ideal, and this is why it's an occurrence obstruction. This is the deeper reason why it is like that. There's no other reason for that. Okay, I think my time's up, right?
Thank you very much, Christian. questions or comments? Please
So you
come up.
proved that F vanishes on that particular tensor, but you wanted to prove that on the G orbit also it vanishes.
Yes, it vanishes not only on the here. It vanishes. No, it's like this. I proved this one here. F vanishes on the F lies in the whole vanishing idea. Yeah.
Okay, that will of course.
Yes. It's not like that tensor only.
Okay, that's true. Exactly. Yeah. No, that.
I didn't understand in what sense it's limited and you can't go beyond like this 3 now. Is it not true with this method construct all?
Yes. So I mean this argument, using only this argument, and by this I mean this argument, the chromatic number is too low. That's a very specific way of proving that these things vanish.
You should mention that you've already gone beyond just simply using.
Oh, sorry. Yes. We are not restricted to this. So with J.M. Landsberg and John Hauenstein, we proved, with using these methods, we proved that the border rank of 2 times 2 matrix multiplication is 7, and we don't use these methods where we. So tableaus get very complicated, and so we use computer support to do that. But that's so we find actually what the partition triple that gives that proves that the border rank of 2 times 2 matrix multiplication is 7, reproving a result by JM from 2004, which.
But I think even in your thesis you went beyond chromatic number, no?
In the thesis, I'm pretty sure this one is by chromatic numbers.
So in this approach, you are just using this conical relation, this Grassmann relations, right? For Fluker relations, you
Yes.
not use that.
No, the other one's not. No, it's just, this one is very limited, but still works. So this one is very, very limited. It's the easiest one to analyze, right? It's completely open how to, there is a lot of leeway. You can go in all directions here. It's very, this is only using very limited techniques at this point.
For example, have you consider using Fluker relations?
The other ones, it becomes complicated. Combinatorics becomes just more involved, right? So, but in principle, yes, that's possible, yes.
Thanks.
So you need to understand straightening somehow.
Yes, but straightening is complicated, yes. But it's exactly the point, yes, straightening is the key point here. And this is nice because you don't need to use straightening, so it works without.
No more questions?
It's interesting that without straightening you could get anything.
Yes, it's not.
It's amazing.
Well, we do a little bit of straightening.
Well, it's just tiny straightening here, right? It's just in the columns.
Not the complicated thing.
Only the easy ones.
Okay. Thank you. Just
Go soon. I just make some money.
Okay, great. Show me the target of the one that is done.